Hello there, and welcome to Sleepy Science Vault. If the Earth simply ceased to exist, not destroyed, not shattered, but simply gone, the first thing to understand is that it would happen in absolute silence. There would be no explosion, no shockwave rippling through the cosmos, no dramatic farewell. One moment the planet is here, the next, it is not. From the perspective of space, the disappearance of Earth would be a quiet event, almost unremarkable to the vast, indifferent universe around it. But for everything on and around the planet, the consequences would be immediate. The very first thing to vanish alongside the Earth would be gravity. Earth's gravitational pull is what keeps you standing, what keeps the oceans in their basins, what holds the atmosphere wrapped around the surface like a thin, delicate skin. The moment Earth disappears, that pull is simply gone. Everything that was resting on the surface, everything floating in the air, everything drifting in the oceans, all of it would be released at once. And because Earth rotates at roughly 1,000 miles per hour at the equator, everything on its surface already has that rotational speed built into it. When gravity lets go, all of that matter, soil, stone, water, air, doesn't just float. It flies. It continues moving in whatever direction it was already heading at the moment of disappearance, launched outward into space like objects released from a spinning wheel. The oceans wouldn't drain away or evaporate. They would slide. Entire bodies of water, billions upon billions of tons of liquid, would shear sideways and drift outward into the void, breaking apart into enormous trembling spheres as surface tension struggled briefly against the vacuum, before those two began to scatter and disperse. The atmosphere would follow. That thin envelope of nitrogen and oxygen and trace gases that makes breath possible, that filters radiation, that creates weather and seasons and the blue color of the sky, it would begin drifting outward into space almost immediately. But not silently. In those final fractions of a second, as the pressure holding the atmosphere together suddenly collapsed, the air itself would generate a sound. A roar, planet-wide, all-encompassing, a pressure wave moving through the last gasps of atmosphere before there was no longer any medium left to carry it. A sound with no one left to hear it. For any human being alive in that moment, there would be no time to process any of this. The human body is built for a very specific set of conditions: pressure, temperature, gravity, breathable air. Remove those conditions all at once, and the body cannot adapt. It cannot survive. The gases dissolved and the blood would expand. The lungs would have nothing to breathe and no pressure to breathe against. The process known as explosive decompression would take hold in seconds, and it would be over very quickly. Not painfully long. Just over. Every living thing would share the same fate. Every creature in the oceans, every insect in the soil, every bird mid-flight, every microorganism clinging to rock faces in the deepest wilderness, all of it extinguished in the same silent, instant event. And that is perhaps the most profound thing to sit with when imagining this scenario. Because Earth is not simply a rock we happen to live on. As far as we know, with every telescope we have ever pointed at the sky, with every signal we have ever sent and never received a reply to, Earth is the only place in the known universe confirmed to harbor life. not just human life. Any life. The only world where chemistry and temperature and water and time came together in precisely the right way to produce something that breathes, grows, feels, and wonders. Scientists sometimes call Earth the cradle of life. And that word, cradle, carries weight. A cradle is where something begins. It is warm and sheltering and specific. You can't just find another one lying around. Every species that has ever existed, every ecosystem that ever flourished, every form of consciousness that ever looked up at the night sky and asked questions about it, all of it emerged from this one small, unremarkable-looking planet, orbiting one average star, in one corner of a galaxy among hundreds of billions. If the Earth disappeared, all of that would disappear with it. Not just the people, not just the animals, but the entire unbroken chain of life stretching back nearly 4 billion years. Gone. Without a trace. Without a sound. The universe would continue on, as it always has, vast and unhurried and silent. There is a kind of quiet miracle in a bee. It moves through the world without any awareness of its own importance, landing on a flower, collecting pollen, moving on to the next. It does not know that in doing so, it is sustaining the food systems that feed billions of people. It does not know that its work underpins the reproduction of somewhere between 70 and 80% of the world's flowering plants. It simply flies, and feeds, and in doing so, keeps a vast portion of the living world in motion. When Earth disappears, the bees go with it. And while that may seem like a small detail in the context of a planet-wide vanishing, it points to something important about the way life on Earth actually works. Everything is connected. Not in a vague, poetic sense, but in a deeply structural, ecological sense. Pollinators maintain flowering plants. Flowering plants feed insects, birds, and mammals. Those animals fertilize soil, disperse seeds, control populations of other species. Remove one thread from that web, and others loosen. Remove the entire web at once, and you begin to appreciate just how intricately, almost impossibly, well constructed it was. Ecosystem services, the term scientists use for all the things the natural world provides to life for free, would simply cease. Clean water filtration through wetlands and root systems. Oxygen production through photosynthesis. Soil stability through root networks and microbial life. Climate regulation through forests and oceans. These are not luxuries. They are the operating conditions for life itself. And they exist only because Earth exists, only because billions of years of geology and biology shaped a world complex enough to sustain them. But perhaps one of the quieter, less obvious losses would be genetic. Every species on Earth carries within it an archive. A biological library written in the language of DNA, accumulated, refined, and diversified over hundreds of millions of years of evolution. The genetic information held within a single species of frog living in an Amazonian rainforest, or a type of grass growing on a mountainside in Central Asia, or a bacterium thriving in a deep-sea hydrothermal vent, each of these contains evolutionary solutions to survival challenges that took millions of years to develop. Resistance to disease. adaptations to extreme temperature, biochemical processes we haven't even begun to study. That information cannot be recreated. It cannot be reverse engineered from scratch. Once it is gone, it is simply gone, permanently and completely. The disappearance of Earth would mean the erasure of the single largest known repository of biological complexity in the universe. Not just the living creatures themselves, but the irreplaceable genetic knowledge encoded within every cell of every organism that ever lived here. It is a loss that goes far beyond what we can easily imagine. And yet, to truly understand what Earth is and what its disappearance would mean, you have to go back much further than life itself. You have to go back to the very beginning, to the formation of the planet. Roughly 4.5 billion years ago, in the region of space that would eventually become our solar system, there was no Earth. There was no Sun yet in its current form, no organized family of planets moving in their familiar orbits. There was only a vast, slowly rotating cloud of gas and dust, the remnants of older stars that had already lived and died, scattered into space as those ancient suns exhausted their fuel and collapsed or exploded. Gravity began to pull this material inward. The center of the cloud grew denser and hotter, eventually igniting into the young star we now call the Sun. But not all of the material fell into the center. A broad, flat disk of gas and dust remained spinning around it, a protoplanetary disk, and within that disk, particles began to collide and stick together. Slowly, incrementally, over millions of years, those collisions built larger and larger clumps of material. Dust became pebbles. Pebbles became boulders. Boulders became planetesimals, rocky bodies large enough to have their own weak gravitational pull. And those planetesimals, in turn, began drawing in more and more material, growing larger, growing warmer, growing more complex. What eventually emerged from this long, violent, gradual process was Earth, a young planet, still molten at its surface, still being bombarded by debris from the forming solar system around it. Barely recognizable as the world we know today. But already, in its basic form, a planet. A world in progress. 4.5 billion years is a number that is genuinely difficult to hold in the mind. If the entire history of Earth were compressed into a single calendar year, modern humans would appear only in the last few minutes of December 31st. The oceans would form in late January. The first simple life would emerge in February. Complex multicellular life wouldn't appear until November. In all of recorded human history, everything we consider civilization would occupy the final few seconds before midnight. The planet is, by any meaningful measure, ancient. And over those billions of years, it did not simply remain a static ball of rock. It evolved. It differentiated. It developed internal structure that is in many ways as complex and dynamic as the surface we inhabit. Today, Earth is not a uniform solid. It is layered, 4 distinct regions, nested inside one another like the layers of an onion, each with its own composition, its own temperature, its own behavior. The outermost layer is the crust, the thin, cool, brittle shell on which all surface geology takes place. Mountains, ocean floors, continents, volcanoes, valleys, All of these exist within the crust. But thin is perhaps an understatement. The thickness of Earth's crust varies significantly depending on where you measure it. Beneath the deep ocean floor, it may be as thin as 5 kilometers, barely more than 3 miles. Beneath the great continental mountain ranges, it can reach up to 100 kilometers. In the grand scale of the planet, the crust is almost negligibly thin, like the skin of an apple, if the apple were nearly 13,000 kilometers across. Beneath the crust lies the mantle, a thick, semi-solid layer of silicate rock that makes up the majority of Earth's volume. This is not liquid rock in the way that lava is liquid. It is more like an extraordinarily viscous solid, one that, over millions of years, flows very slowly under heat and pressure. The mantle is the engine behind plate tectonics, the slow churning process that moves the continents, builds mountains, triggers earthquakes, and recycles the crust itself over geological timescales. Deeper still, you encounter something genuinely remarkable: the outer core. Unlike the mantle, the outer core is truly liquid. It is composed primarily of iron and nickel, kept in a molten state by the intense heat radiating from deeper within the planet, and by the residual heat left over from Earth's formation billions of years ago. This liquid metal layer is in constant motion, flowing in great currents driven by temperature differences and by Earth's rotation. And it is precisely that motion that generates something every compass on Earth depends on: the planet's magnetic field. Earth's magnetosphere is, in one sense, invisible and intangible. You cannot see it. You cannot feel it. But it is one of the most important protective structures on the planet. It deflects the solar wind, the constant stream of charged particles pouring outward from the sun, and redirects it around the Earth rather than allowing it to strip away the atmosphere. Without the magnetic field generated by that moving liquid iron in the outer core, Earth's atmosphere would erode over time, much the way Mars's thin atmosphere is thought to have been lost billions of years ago. And at the very center of all of this, beneath the mantle, beneath the liquid outer core, sits the inner core. It is a solid sphere, approximately 759 miles in diameter, composed of iron and nickel compressed under such extreme pressure that despite the extraordinary heat surrounding it, it cannot melt. The density of material at the inner core is roughly 16 grams per cubic centimeter. For comparison, water is 1 gram per cubic centimeter, and even solid iron at the surface sits at around 7.8. The inner core is extraordinarily compressed, squeezed into rigidity by the weight of everything above it. The temperature at the inner core is estimated to range between 9,000 and 13,000 degrees Fahrenheit. To give that some context, the surface of the Sun is approximately 10,000 degrees Fahrenheit. The center of our planet is, in other words, roughly as hot as the visible surface of a star. It sits there, at the center of everything we have ever known, beneath every city, every ocean, every mountain range, every creature that has ever walked or swum or flown, silent, unreachable, extraordinarily hot, and extraordinarily dense. A solid iron heart, keeping time with the slow rhythms of a world in constant, subtle motion. If the Earth disappeared, all of this would go with it. Not just the surface, not just the landscapes and the living things, but 4.5 billion years of geological formation. the slow process of differentiation that separated heavy metals from lighter rock. The liquid iron engine generating the magnetic field. The deep mantle currents driving the continents. The compressed, heat-blazing solid core sitting at the very center of it all. Every layer, every process, every ancient structure built up over timescales the human mind can barely begin to grasp. Just gone. And the universe would have one fewer world to speak of. Beneath the crust, beneath everything we can see or touch or drill down into, lies a layer of rock so vast that it almost defies description. The mantle stretches nearly 2,900 kilometers from top to bottom, a shell of silicate rock that makes up roughly 84% of Earth's total volume. If you could somehow remove everything else, the crust above, the core below, and hold the mantle on its own, it would dwarf everything you'd taken away. It is the dominant structure of the planet, the great bulk of what Earth actually is. And yet most people will go their entire lives without thinking about it once. The mantle is not dramatic in the way volcanoes are dramatic, or earthquakes, or storms. It does not move quickly enough to be visible. It does not announce itself. But it is the reason any of those dramatic things happen at all. It is the slow, hidden engine beneath everything. To understand the mantle, you have to let go of the idea that rock is rigid. At the surface, of course, rock behaves the way we expect, hard, fixed, immovable on any human timescale. But deep in the mantle, under conditions of immense heat and pressure, rock behaves differently. It becomes, as geophysicists sometimes describe it, almost squishy. Not liquid, it does not flow like water or even like lava at the surface. But given enough time and enough pressure, it deforms. It creeps. It moves. Think of it like an extraordinarily thick, slow-moving fluid. Something closer in behavior to glacial ice than to the stone you might pick up from a riverbed. On human timescales, it appears completely motionless. But on geological timescales, millions and hundreds of millions of years, the mantle flows. This process is called convection, and it is happening right now, far beneath your feet. Heat from the core radiates outward into the lower mantle, warming the rock there. Warmer rock is slightly less dense than the cooler rock above it, so it rises, very slowly, over millions of years, toward the upper mantle. As it rises and cools, it becomes denser again, and eventually sinks back down toward the core. Then the cycle begins again. Great, slow loops of moving rock, circulating through the interior of the planet on timescales that make human civilization look like the blink of an eye. It is this convection, this slow churning of the mantle, that drives plate tectonics. The crust of the Earth is not a single, continuous shell. It is broken into a series of massive fragments called tectonic plates, and those plates are in constant, slow motion, carried along by the movements of the mantle beneath them. Where plates pull apart, new crust is created as magma rises to fill the gap. Where plates collide, mountain ranges are pushed upward, or one plate is driven beneath the other and consumed back into the mantle. Where plates slide past each other, the grinding friction produces earthquakes. Every major mountain range on Earth was built by plate tectonics. The Himalayas, still rising today, formed from the slow-motion collision of the Indian subcontinent with the Eurasian plate, a collision that began around 50 million years ago and has not yet finished. The Andes, the Alps, the Rockies, all of them ultimately products of convecting mantle rock and the plates it carries. Without the mantle's convection, plate tectonics would stop. The plates would lock in place. Over millions of years, volcanic activity would decline sharply. The recycling of the crust, the process by which old rock is pulled back into the mantle and new rock is generated, would cease. The surface of the planet would become geologically static and, over time, increasingly inhospitable to complex life. If Earth disappeared, all of this motion, billions of years of it, continuing still, would simply stop. Not slow down. Not wind down gradually. Just stop, all at once, as the planet carrying it ceased to exist. One of the most vivid expressions of plate tectonics is something most people have never seen, and never will, the mid-ocean ridge system. Spread across the floors of the world's oceans is the longest mountain range on Earth, and it is almost entirely underwater. The mid-ocean ridge stretches roughly 40,000 miles, wrapping around the planet like the seam of a tennis ball, running through the Atlantic, the Indian Ocean, the Pacific, and connecting into a single, continuous geological feature. It is, by length and by scale, the most dramatic mountain range on the planet. And almost no one thinks about it. At the mid-ocean ridge, tectonic plates are pulling apart, and magma from the mantle rises continuously to fill the gap. As it meets the cold seawater, it solidifies into new ocean crust, fresh rock, being created in geological real time, spreading the seafloor outward from the ridge in both directions. This is where new Earth is literally being made. And along those ridges, in environments that would seem completely hostile to life, ecosystems thrive. Hydrothermal vents, cracks in the seafloor through which superheated, mineral-rich water pours, support entire communities of organisms that have never seen sunlight. Tube worms, giant clams, unique species of shrimp and fish and microbial mats. Life, in one of the most extreme environments on the planet, sustained entirely by the heat and chemistry of the Earth's interior. The mid-ocean ridge and its ecosystems represent something profound, evidence that life on Earth is not only a surface phenomenon. It extends into the deep ocean, into the cracks of the seafloor, into places far from the sun's warmth. Places powered, instead, by the planet itself. At the other end of the visibility spectrum are coral reefs, perhaps the most visually celebrated ecosystems on Earth. Coral reefs cover less than 1% of the ocean floor, yet they support an estimated 25% of all marine species. They are among the most biologically diverse environments on the planet, dense, layered, extraordinarily complex communities where fish and crustaceans and mollusks and echinoderms and hundreds of other forms of life interact in relationships built up over millions of years. They produce food and income for hundreds of millions of people. They protect coastlines from erosion and storm surge. They are, in many respects, the rainforests of the sea. And they exist only because of a very precise set of conditions: warm, shallow, clear water, specific mineral content, the right temperature range, adequate sunlight. conditions that exist only on a planet like Earth. The coral animals themselves, tiny, soft-bodied organisms, build their calcium carbonate skeletons over centuries and millennia, constructing physical structures large enough to be visible from space. The Great Barrier Reef, the largest living structure on Earth, took tens of thousands of years to form in its current configuration. It is not just an ecosystem, it is also a geological record, a vast archive of climate and oceanographic history preserved in the structure of the reef itself. If Earth disappeared, the coral reefs would vanish with it. Not just the living animals, but the physical structures they built, the accumulated work of millions of years of biological construction, gone in an instant. And then there's Antarctica. There's nowhere else on Earth quite like it. The southernmost continent is a place of such extremes that even describing it requires a kind of recalibration of expectations. It is the coldest continent, the driest continent, the windiest continent, and the highest continent. Its average elevation is greater than any other landmass on Earth, largely because of the ice sheet that covers it. That ice sheet, in places nearly 3 miles thick, contains approximately 60% of the world's fresh water. If it were to melt entirely, which current science suggests would take thousands of years under warming conditions, global sea levels would rise by roughly 60 meters. Enough to submerge the majority of the world's coastal cities. Antarctica is also a continent of records. The lowest natural temperature ever recorded on Earth, -89.2 degrees Celsius, was measured at a Soviet research station there in 1983. Wind speeds at some coastal locations have exceeded 300 kilometers per hour. In the interior, there are places that receive so little precipitation that they are technically classified as desert, despite being covered in ice. Beneath that ice, hidden from the surface for millions of years, are subglacial lakes, bodies of liquid water kept from freezing by the pressure of the ice above and by geothermal heat from below. Lake Vostok, the largest of these, is roughly the size of Lake Ontario, and has been sealed from the surface for somewhere between 15 and 30 million years. Scientists suspect it may harbor microbial life, organisms adapted to conditions of complete darkness, extreme cold, and total isolation that have evolved independently of the surface world for geological ages. Antarctica is also scientifically irreplaceable in another sense. Its ice cores are among the most valuable climate records we have. Trapped within the layers of ice are ancient air bubbles, tiny pockets of atmosphere preserved from hundreds of thousands of years ago. By analyzing these bubbles, scientists can directly measure the composition of Earth's past atmosphere, reconstruct temperature records, and understand how the climate has changed over deep time. It is, in a very literal sense, a library of Earth's atmospheric history. Written in ice, buried under miles of it, waiting patiently to be read. All of this, the ice sheet, the subglacial lakes, the wind-scoured valleys, the ancient frozen air, the extraordinary and unique organisms that have adapted to survive there, would simply vanish if the Earth did. Which brings us, gently, away from the surface and outward into space. Because when a planet disappears, the story doesn't end there. Physics has a kind of memory, and the consequences of Earth's disappearance would extend far beyond the planet itself. At this very moment, Earth is moving. It has always been moving. It orbits the Sun in a path that takes roughly 365 days to complete, and to maintain that orbit, it moves at a speed that is difficult to fully absorb, approximately 18.5 miles per second. Not miles per hour. Miles per second. That is fast enough to cross the continental United States in under 3 minutes. Fast enough to travel from the Earth to the Moon in less than 6 hours. It is the speed that our planet has maintained for 4.5 billion years, held in its orbit by the gravitational balance between Earth's momentum and the Sun's gravitational pull. Now, Newton's first law of motion states that an object in motion stays in motion unless acted on by an external force. Earth's orbital velocity is, in this sense, a stored property, a momentum that belongs to the planet, carried by every atom of it. If Earth were to suddenly disappear, that momentum would not disappear with it. Every piece of matter that had been part of Earth, every grain of rock, every drop of ocean water, every wisp of atmosphere, would continue moving at 18.5 miles per second in the direction it was already heading at the moment of disappearance. Rather than an orbit, a curved path maintained by gravity, all of that matter would travel in straight lines, or rather in the gentle curves imposed by whatever other gravitational influences remained in the solar system. The material would disperse, slowly spreading outward, no longer bound to a common center. There would be no orbit anymore. Because an orbit requires a planet. And the planet would be gone. What had been Earth, that ancient, layered, living, complex world, would become, in time, a diffuse region of scattered material, thinning as it spread, losing coherence with every passing year, until eventually there was nothing you could point to and say, there. That was once a planet. Just the quiet of space. And the sun, still burning, circling its own path around the galaxy, looking, if a star could look, for something that was no longer there. The moon has been with us for a very long time. Current scientific understanding places its formation at roughly 4.5 billion years ago, not long after Earth itself formed, the result of a collision between the young Earth and a Mars-sized body that scientists have named Theia. The impact was catastrophic by any measure, sending an enormous plume of vaporized rock into orbit around the damaged Earth. Over time, that debris coalesced under its own gravity, cooled, and became the moon, our companion, our tidal engine, the most familiar object in the night sky. For all of those billions of years, the moon has been held in place by Earth's gravity. It does not stay in orbit because of any intrinsic desire to do so. It stays because Earth is pulling on it, and the moon's forward momentum is precisely balanced against that pull, creating the stable, roughly circular orbit that keeps it at an average distance of about 239,000 miles from the surface. That balance is extraordinarily precise. And it depends entirely on Earth being there. The moment Earth disappears, the gravitational anchor holding the moon in orbit is gone. There is nothing pulling it inward anymore. Nothing curving its path. And so the moon does what any object does when the force constraining it is suddenly removed. It continues in the direction it was already moving. It flies off in a straight line. Not dramatically. Not explosively. There would be no visible change in the first moment, no lurch, no shudder. The moon would simply continue along the tangent of its orbit, that straight line path that the curve of its orbit was always pulling it away from. And it would keep going. Out into the solar system, away from the region of space where Earth used to be, moving at roughly 1 kilometer per second, the orbital speed it had maintained for billions of years, now carrying it not around a planet, but simply away. Where would it go? That depends on the gravitational landscape of the solar system around it. Jupiter, the largest planet in our solar system, exerts an enormous gravitational influence over a wide region of space. Depending on the moon's trajectory at the moment of Earth's disappearance, Jupiter's gravity could eventually capture it, deflect it into a new orbit around the Sun, or send it on a long curved path through the inner solar system. Saturn, too, has captured moons before, or at least is believed to have, based on the unusual characteristics of some of its smaller satellites. The moon might, in time, find a new gravitational home. It might settle into orbit around another planet, becoming one more moon among many in a solar system already rich with them. Jupiter alone has nearly 100 confirmed moons. Saturn has over 140. One more, arriving from the inner solar system, would not be especially remarkable from an astronomical perspective. But there is something else worth considering, something that makes the moon's departure more than just a question of orbital mechanics. For as long as Earth has had complex life, the moon has been doing something that rarely gets acknowledged. It has been stabilizing the planet's axial tilt. Earth currently rotates on an axis tilted at approximately 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us seasons, the northern hemisphere leaning toward the Sun in summer, away from it in winter. That tilt has remained relatively stable throughout the history of complex life on Earth, varying only slightly over long timescales due to the gravitational influence of other planets. The moon is a significant reason for that stability. Its gravitational pull acts as a kind of gyroscopic damper on Earth's wobble, preventing the kind of wild, chaotic variations in axial tilt that a planet without such a large moon might experience. Without the moon, over millions of years, Earth's axial tilt could vary dramatically. Some models suggest it could swing anywhere from near zero to more than 80 degrees. A near-zero tilt would mean almost no seasons, the poles would remain cold year-round, the equator perpetually hot, with little of the seasonal cycling that drives so much of Earth's ecological and meteorological behavior. A tilt approaching 90 degrees would be far more extreme. The poles would bake in continuous sunlight for half the year, then freeze in complete darkness for the other half. The climate would be almost unrecognizable. In the scenario where Earth disappears, of course, this is moot. There is no Earth left to tilt. But it is a reminder of how deeply interconnected Earth's conditions are with the presence of the moon, and how many things we take for granted about this planet are quietly maintained by systems and relationships most of us never think about. Now let's step back even further. Let's look at the rest of the solar system and ask a question that might seem almost counterintuitive at first. Would anything out there actually notice? The Sun, for its part, would not. This is not a poetic statement. It is a physical one. The Sun is so vastly, incomprehensibly larger than Earth, that the removal of our planet from the solar system would have essentially no detectable effect on it. The Sun contains approximately 99.8% of all the mass in the entire solar system. Jupiter accounts for most of the remaining fraction. Earth, by comparison, is almost negligibly small in the context of solar system mass. The Sun would continue burning. It would continue fusing hydrogen into helium at its core, as it has for 4.5 billion years, with a lifespan of another 5 billion years still ahead of it. Its output, the constant flood of light and heat and radiation pouring outward in all directions, would be completely unaffected. The tiny gravitational contribution that Earth made to the solar system's overall mass distribution would be gone, but the effect on the Sun's behavior would be, for all practical purposes, unmeasurable. The Sun does not need Earth. It never did. The other planets would be similarly indifferent, in a mechanical sense. Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all of them orbit the Sun in paths determined primarily by the Sun's gravity and their own momentum. Earth's gravitational influence on them is real but small, and its removal would cause only the most minute adjustments to their orbits over very long timescales. The kind of adjustments that would take millions of years to accumulate into anything measurable. Mars would continue its slow, elliptical orbit. Jupiter would keep shepherding the asteroid belt with its enormous gravity, as it has done throughout the solar system's history. Saturn's rings would catch the sunlight. Neptune would continue its 265-year journey around the Sun, so far from the center that even one full orbit takes longer than recorded human history. The planets would keep moving. Normally. Predictably. Gracefully. As they have always moved. And that, somehow, is one of the most quietly affecting aspects of this entire scenario. Because from the perspective of the solar system as a whole, from the perspective of physics and orbital mechanics and stellar dynamics, the disappearance of Earth would be a remarkably minor event. A small adjustment. A rounding error in the gravitational accounts of the Sun's family of worlds. Only us would be gone. Everything else would continue. The Sun would rise and set on the surface of Mars, even though there would be no one on Earth watching it rise on theirs. Jupiter's storms would continue churning. The ice geysers of Enceladus would keep erupting into Saturn's orbit. The solar wind would keep blowing outward through the solar system, unimpeded now in the region where Earth's magnetosphere used to divert it. The solar system would simply have one fewer planet. The count, for whatever record-keeping the universe keeps, would drop by 1. 8 planets instead of 9, or 8 instead of what we currently call 8, depending on how you feel about Pluto. But it would also lose something less categorical and harder to quantify. Earth contributes approximately 9.2 times 10 to the power of 24 kilograms to the total mass of the solar system. Written out, that is roughly 6 billion trillion metric tons. It is a number so large it becomes almost abstract. And yet in the context of the solar system's total mass, dominated so completely by the Sun, it represents less than 1,000th of a percent of the whole. Removing it would change the solar system's total mass budget by an amount so small that it would have no meaningful effect on anything, not on the sun's gravity, not on the orbital paths of the remaining planets, not on the behavior of the asteroid belt or the distant Kuiper belt objects drifting in the cold outer reaches of the solar system. The sun's gravity, which extends across the entire solar system and beyond, would simply no longer have Earth to act upon in the way it once did. It would still extend through the region of space where Earth used to orbit. It would still exert force on anything passing through that region. But there would be nothing there to hold an orbit, nothing there to warm, nothing there to illuminate with that 8-minute-old light that used to fall every morning across oceans and mountains and open plains. The light would still travel outward. It would pass through the region where Earth used to be, and continue on into deeper space, as if nothing had ever been there to receive it. That image is worth sitting with for a moment. Sunlight that used to fall on forests and deserts and Arctic ice, that used to scatter through the atmosphere into the blue of the sky, that used to warm the surface of the ocean and drive the entire cycle of weather and evaporation and rain, all of that light would still be produced, still travel outward at 300,000 kilometers per second, still reach the orbital distance where Earth once moved through space, and then pass through, illuminating nothing. It is in that image, perhaps, that the true weight of Earth's disappearance reveals itself most clearly. Not in the physics, not in the orbital mechanics, not in the mass calculations or the gravitational adjustments, but in the simple fact that there would be no one left to see the light. The solar system would continue its ancient, beautiful, unhurried motions. Stars would rise and set on other worlds. Ice would crack and reform on frozen moons. Gas giants would spin, and storm, and shine in the reflected light of a sun that continues burning without audience or witness. And where Earth once was, that particular patch of space, that specific orbital path traced year after year for 4.5 billion years, there would simply be nothing. Just the quiet hum of a solar system going about its business, one world lighter than before. There is a particular quality to Earth's atmosphere that only becomes apparent when you try to imagine a planet without one. Most planets in our solar system have no meaningful atmosphere at all, or have one so thin or so toxic that it bears almost no resemblance to the envelope of air surrounding our world. Mars has an atmosphere roughly 1% as dense as Earth's, composed mostly of carbon dioxide, offering almost no protection from radiation and no capacity to retain warmth. Venus has a thick atmosphere, but one so laden with carbon dioxide and sulfuric acid that its surface temperature exceeds 460 degrees Celsius, hotter than Mercury, despite being farther from the Sun. The outer planets have their own atmospheric compositions, their own pressures and temperatures, utterly inhospitable to life as we understand it. Earth's atmosphere is something else entirely. It is a finely balanced system, one that took billions of years to reach its current composition, shaped by geological processes, by the evolution of photosynthetic life, by the slow interplay between the planet's interior and its surface. And the result is a layer of gas that does something remarkable. It keeps the planet warm. Not by trapping all of the sun's heat, but by managing it. Sunlight passes through the atmosphere relatively freely, warming the surface. That warmth then radiates back upward as infrared radiation, heat. And certain gases in the atmosphere, the greenhouse gases, water vapor, carbon dioxide, methane, nitrous oxide, absorb some of that outgoing heat and radiate it back downward. The effect is a kind of thermal blanket, maintaining surface temperatures that are significantly warmer than they would be on a planet with no atmosphere at all. Without this greenhouse effect, Earth's average surface temperature would be somewhere around -18 degrees Celsius. With it, the average is approximately 14 degrees Celsius, roughly 57 degrees Fahrenheit. That difference, those 30+ degrees of warming provided by the atmosphere, is the difference between a planet covered in ice and a planet teeming with life. It is easy to take that warmth for granted. It is simply the temperature of the world. But it is not a given. It is the product of a very specific atmospheric composition, maintained over very long timescales, on a planet the right distance from the right kind of star. That atmosphere is composed primarily of nitrogen, roughly 78%, and oxygen, approximately 21%. The remaining 1% is a mixture of argon, carbon dioxide, water vapor, and trace amounts of other gases. The nitrogen is largely inert, providing mass and pressure without participating actively in most biological or chemical processes at the surface. The oxygen is the breath of the biosphere, produced almost entirely by photosynthetic life, consumed by animals and by combustion, cycling continuously through living organisms, the oceans, and the atmosphere in a balance maintained over geological time. For all its importance, the atmosphere is remarkably thin. 90% of the total mass of Earth's atmosphere sits within the first 10 miles above the surface. 10 miles is not far. If you drove a car straight upward at highway speed, you would pass through 90% of the atmosphere in less than 10 minutes. The remaining 10% extends further: the stratosphere, the mesosphere, the thermosphere, the exosphere, growing progressively thinner with altitude until it fades imperceptibly into the vacuum of space, with no clear boundary where atmosphere ends and space begins. This thinness is part of what makes the atmosphere so vulnerable. It is not a deep, robust ocean of gas. It is a delicate skin, held against the planet by gravity, warmed by the greenhouse effect, maintained by the continuous output of photosynthetic life. Remove any of those conditions, and it begins to erode. If Earth disappeared, the atmosphere would be released all at once, no longer held in place, no longer warmed by a surface below it, no longer replenished by the life that produces its oxygen. It would disperse into space with the rest of the planet's matter, and the particular balance of gases that made breath possible, that made the sky blue, that kept the surface warm enough for liquid water, would cease to exist. And liquid water, of course, is something Earth has in extraordinary abundance. Roughly 70% of Earth's surface is covered by ocean. Seen from space, the planet appears predominantly blue, a world defined as much by its water as by its land. The total volume of water on Earth is staggering, enough to cover the entire surface of the planet to a depth of about 2.5 kilometers if spread evenly. And of all that water, approximately 97% sits in the oceans, salt water, vast and deep, circulating in global currents that distribute heat around the planet and regulate climate on timescales ranging from years to millennia. The oceans are not simply bodies of water. They are dynamic systems, absorbing carbon dioxide from the atmosphere, producing oxygen through marine photosynthesis, transferring heat from the tropics toward the poles, influencing weather patterns across entire continents. The moisture that falls as rain over the Amazon rainforest originated largely in the Atlantic Ocean. The warmth that keeps northern Europe habitable despite its latitude is carried there by ocean currents. The monsoons that bring life-sustaining rainfall to South Asia are driven by the differential heating of ocean and land. The oceans are also the cradle within the cradle, the environment in which life on Earth first appeared, and in which the majority of Earth's biodiversity still resides. The deep ocean remains one of the least explored environments on the planet. We have more detailed maps of the surface of Mars than of the ocean floor. Whatever lives in those depths, and the evidence suggests it is a great deal, much of it remains unknown to us. In recent centuries, human industrial activity has been adding greenhouse gases to the atmosphere at a rate faster than the natural carbon cycle can absorb them. Carbon dioxide levels, methane levels, nitrous oxide levels, all have increased significantly since the beginning of the industrial era. The measured effect of this accumulation is a warming of the global average surface temperature by approximately 0.8 degrees Fahrenheit relative to pre-industrial baselines. 0.8 degrees sounds small. In everyday experience, it is a change you would barely notice stepping outside. But applied across the entire surface of a planet, across every ocean, every ice sheet, every ecosystem, it is an enormous amount of energy. It is enough to shift precipitation patterns, to accelerate glacier retreat, to alter the timing of seasons in ways that cascade through ecosystems. The atmosphere is sensitive to relatively small changes in its composition, because those changes affect how much heat it retains, and heat distributed across a planetary surface operates on a scale where even fractional changes carry significant consequences. But all of this, the greenhouse effect, the warmth, the oceans, the rainfall, the cycling of carbon and oxygen, all of it depends on something that is easy to overlook, because it is invisible and intangible and operates entirely beyond the range of human senses. It depends on the magnetic field. We have touched on this already, in discussing the liquid iron outer core and its role in generating Earth's magnetosphere. But it is worth dwelling on, because the magnetic field is one of the most important and least appreciated features of this planet. The magnetosphere extends far out into space around Earth, not as a perfect sphere, but as a teardrop shape, compressed on the sunward side and stretched into a long tail on the opposite side by the constant pressure of the solar wind. At its widest, it extends roughly 65,000 kilometers toward the Sun and many times that distance on the far side. And it acts as a shield. The solar wind is a continuous stream of charged particles, electrons, protons, alpha particles, flowing outward from the Sun at speeds of several hundred kilometers per second. Without a protective magnetic field, these particles would bombard Earth's upper atmosphere directly, gradually stripping it away through a process called atmospheric sputtering. This is precisely what happened to Mars, a planet that once had a magnetic field and lost it billions of years ago when its smaller iron core cooled and solidified. With no magnetic field, the Martian atmosphere was slowly eroded by the solar wind over geological time, until what remained was the thin, cold, radiation-exposed shell it is today. Earth's magnetic field prevents this from happening here. The charged particles of the solar wind are deflected around the planet, guided by the field lines away from the atmosphere, channeled toward the polar regions where they interact with atmospheric gases to produce the auroras, those curtains of green and red and purple light that shimmer in the high-latitude sky. The aurora is, in one sense, a visible record of the solar wind meeting Earth's defenses. A side effect of protection, made luminous. The magnetosphere also shields the surface from a portion of the cosmic radiation that pervades space, high-energy particles originating from distant supernovae and other extreme astrophysical events. Without this shielding, surface radiation levels would be significantly higher, with potentially severe consequences for complex life. When Earth disappears, the magnetic field disappears with it. The liquid iron outer core that generates it, that vast, slowly churning engine of conducting fluid deep within the planet, is gone. The magnetosphere, which has been deflecting the solar wind for billions of years, collapses instantly. There is no longer anything to deflect. There is no longer any atmosphere to protect. There is no longer any surface for radiation to reach. The solar wind simply flows through the region of space where Earth once orbited, unimpeded, as if the planet had never been there. The auroras, those beautiful, silent performances of light at the edges of the polar skies, they would not happen anymore. Not above Earth, at least. Not in that particular region of space, at that particular orbital distance, in those particular colors produced by the specific mixture of nitrogen and oxygen in that specific atmosphere. That particular light show, repeated in various forms for hundreds of millions of years, visible from the surface of a planet alive with things capable of looking up and being moved by beauty, that would be over. The solar wind would continue blowing. The sun would continue generating it, as it will for billions of years to come. But there would be nothing in that part of space to glow in response to it. Nothing to be lit up. Nothing to be defended. Just the stream of particles, passing through empty space, carrying on as they always have, indifferent, relentless, and utterly unaware of what was once there to meet them. There is something almost poetic about a compass. A small, simple instrument, a magnetized needle balanced on a point, free to rotate, and yet for centuries it was one of the most important navigational tools in human history. It worked because of something invisible, something extending tens of thousands of kilometers out into space from the liquid iron heart of the planet. The compass needle didn't point north because of anything in the needle itself. It pointed north because Earth's magnetic field gave it somewhere to point. If Earth disappeared, compasses would become, in an instant, perfectly useless. Not broken, exactly. The needle would still be magnetized. It would still be free to rotate. But there would be nothing for it to align with. No field. No north. No south. Just a needle drifting freely, with no orientation in a universe that no longer had an Earth to orient itself toward. It is a small image, but a telling one. So many things we rely on, so many instruments, systems, technologies, and instincts, are quietly calibrated to the presence of this planet and the invisible fields it generates. Remove the planet, and all of those calibrations become meaningless all at once. Before Earth disappeared, there would be one final, extraordinary atmospheric event worth imagining. As the magnetic field began to fail, in whatever hypothetical scenario allows for even a brief transition, the protection it provided to the upper atmosphere would weaken, and the solar wind would begin to penetrate further and further toward the surface. The result would be auroras unlike anything ever seen in human history. Normally, auroras are a phenomenon of the polar regions. The magnetic field funnels the solar wind particles toward the poles, and it is there, above the Arctic tundra, above the Antarctic ice, in the high latitudes of Scandinavia and Alaska and southern Chile, that the atmosphere lights up in those famous curtains of color. The further you are from the poles, the less likely you are to see them. At the equator, under normal conditions, an aurora is essentially never visible. But as the magnetic field collapsed, the solar wind would no longer be channeled. It would strike the atmosphere at all latitudes simultaneously. Auroras would appear over the tropics, over the deserts, over the open ocean at the equator. They would spread across the entire sky, not just at the poles but everywhere, a planet-wide display of shifting light. Green, red, blue, purple, the colors determined by which atmospheric gases the particles were exciting, at which altitudes. For a brief moment, the whole sky would glow. It would be, by any measure, one of the most spectacular light displays in the history of the planet. And there would be no one left afterward to describe having seen it. Now, most people are familiar with gravity. Most people have at least a passing familiarity with Earth's magnetic field. But there is a third fundamental field associated with this planet that almost never comes up in casual conversation, and yet is quietly essential to the atmosphere and to life. Earth has a global electric field. It exists between the surface of the planet and the upper atmosphere, specifically the ionosphere, a layer of the atmosphere where solar radiation ionizes gas molecules, creating a region rich in free electrons and ions. The surface of the Earth carries a slight negative charge. The ionosphere carries a positive charge. Between them, a voltage difference exists, approximately 300,000 volts across the full height of the atmosphere, which works out to an average electric field strength of roughly 100 volts per meter near the surface. In practical terms, this means there is always a weak downward-pointing electric force near Earth's surface. And this field, though far weaker than gravity in terms of the forces most of us notice in daily life, has a measurable and important effect. For small, charged particles in the atmosphere, ions, fine aerosols, certain types of atmospheric particles, the electric field acts as a kind of conveyor belt. It moves charged material vertically through the atmosphere, separating particles of different charges, influencing where they accumulate and how they behave. This process is deeply involved in cloud formation, in the global electrical circuit, and in the chemical processes that determine the composition of the air at different altitudes. Here is one of the more striking numbers associated with this field. For a charged particle of a certain size, A proton, for instance, the upward electric force exerted by Earth's global electric field is approximately 10.6 times greater than the downward gravitational force acting on that same particle. The electric field, for small charged particles, doesn't just compete with gravity. It overwhelms it. It lifts material upward that gravity would otherwise pull down. This has real consequences for the upper atmosphere. The distribution of ions in the ionosphere, the behavior of the solar wind as it interacts with Earth's outermost atmospheric layers, the way certain elements and molecules are retained or lost, all of these are influenced by the electric field. It is one of the reasons Earth's atmosphere has the composition it does. Scientists sometimes describe Earth as uniquely possessing three fundamental planetary energy fields operating simultaneously: gravitational, magnetic, and electric, each interacting with the others, each shaping the environment in ways that individually would be significant but together create something considerably more complex and stable than any one of them could produce alone. Gravity holds the atmosphere against the surface, prevents the oceans from drifting into space, keeps the planet in orbit around the sun. The magnetic field shields the atmosphere from the erosive force of the solar wind, deflecting charged particles away from the surface. And the electric field manages the vertical distribution of charged material within the atmosphere, influencing cloud formation, chemical composition, and the behavior of the ionosphere. Remove any one of these, and the atmosphere as we know it would, over time, be unrecognizable. Remove all three at once, as Earth's disappearance would do, and the atmosphere ceases to exist in any meaningful form almost immediately. The air we breathe is not simply air. It is the product of gravity, magnetism, and electricity working together over billions of years, on a planet that happened to have all three in the right proportions and the right configurations. The oxygen in your lungs right now is there because of processes that required all of those fields simultaneously. The nitrogen, the water vapor, the trace gases, their presence at the surface, their behavior in the atmosphere, their role in supporting life, all of it is shaped by this triple interaction that, as far as we currently know, exists in this particular combination on exactly one planet in the observable universe. Earth's global electric field is just as vital to the living world as the more famous forces that share the planet with it. It simply has a much lower profile. If Earth disappeared, the electric field would vanish with it. The surface charge, the ionospheric charge, the voltage gradient stretching through the atmosphere, all of it would dissolve in an instant, along with the atmosphere it helped to shape. The global electrical circuit that connects thunderstorms to the ionosphere, that moves charge continuously around the planet in patterns scientists are still working to fully understand, gone, without a trace. And now, having spent time with the physics in the atmosphere and the deep invisible forces that made this planet what it was, it is worth pausing briefly to consider the human dimension of all this. Not the physics of disappearance, but the imagination of survival. Because human beings have a remarkable tendency, when faced with existential challenges, to immediately start problem solving. If words somehow reached humanity in advance, if we knew, with certainty, that the Earth was going to vanish, the response would be extraordinary. Not organized, necessarily. Not calm. but extraordinary in its urgency and its creativity and its sheer, stubborn refusal to simply accept the end. And where would people look? The same place humans have been looking for decades when imagining a future beyond Earth. Mars. Mars is, by most measures, a deeply inhospitable place. Its atmosphere is thin and unbreathable, mostly carbon dioxide. Its surface is cold, dry, and exposed to radiation levels that would be dangerous for long-term human habitation without substantial shielding. Its gravity is about 38% of Earth's, with uncertain long-term effects on human physiology. There is no liquid water on the surface. There are no ecosystems, no food sources, no breathable air. And yet, Mars is the most accessible alternative to Earth in our solar system. It is rocky. It has a day length remarkably similar to Earth's, 24 hours and 37 minutes. It has polar ice caps. It has geological evidence of a warmer, wetter past. It has been the subject of more robotic exploration than any other planet, and it is the destination most seriously considered for eventual human settlement. In the scenario where Earth's disappearance was known in advance, Mars real estate, theoretical as it currently is, would presumably become the most sought-after commodity in the history of human civilization. The irony of applying concepts like property ownership and market value to a planet with no infrastructure, no breathable atmosphere, and no existing human presence would be almost entirely lost in the panic and urgency of the situation. People would buy claims. Governments would stake territories. Companies would compete for contracts to build the first habitable structures. Whether any of it would be livable in time is a separate question. But the impulse to claim a piece of the next world before it runs out would be entirely, recognizably human. And along with the real estate market, another industry would see demand unlike anything in its history. Spacesuit manufacturing. A spacesuit is an extraordinary piece of engineering. It is, in essence, a wearable spacecraft, a self-contained environment that maintains pressure, temperature, oxygen supply, carbon dioxide removal, and radiation protection for the human body in conditions where all of those things are otherwise absent. A modern extravehicular suit used by astronauts on spacewalks is the product of decades of development, incorporates hundreds of individual components, and takes years to design and test for a single mission. In a world facing the disappearance of Earth, the demand for personal life support systems would be instant and overwhelming. Not just for travel to Mars, but for survival and transit, for life aboard whatever space stations or spacecraft could be hastily expanded or constructed, for any environment where the comfortable bubble of Earth's atmosphere was no longer available. The gap between demand and supply would be almost incomprehensible. The entire global output of spacesuit manufacturing, currently measured in dozens of units per year, would need to scale by factors of millions almost overnight. It would be one of the starkest illustrations of how thoroughly unprepared the human species currently is for existence beyond this planet. We have built everything, every city, every road, every satellite, every cultural institution, every system of government and trade and communication, on the assumption that Earth would always be here. That the air would always be breathable. That the ground would always be underfoot. that gravity would always hold us in place. The space suits, the Mars property, the scramble for survival, all of it points to the same underlying truth. Humans are creatures of Earth in the most complete and literal sense. We are not adapted to space. We are not equipped, physically or logistically, for life without a planet beneath us. We have begun, tentatively, to imagine what it might mean to live elsewhere. But we are at the very earliest stages of that imagination becoming reality. Earth is not just where we live. It is what we are built for. Every aspect of human biology, our bone density calibrated for Earth's gravity, our lungs shaped for Earth's atmospheric pressure and composition, our circadian rhythms tuned to Earth's rotation rate, our temperature regulation calibrated for Earth's climate range, all of it is an expression of deep evolutionary adaptation to this specific planet. Remove the planet, and you don't just remove the home. You remove the environment that every human being is fundamentally, biologically designed to inhabit. The compasses would stop pointing. The auroras would spread across every sky. The electric field would dissolve. The atmosphere would disperse. And the most complex, inventive, restless species the planet ever produced would find itself, for the first time in its existence, without the world it was made for. Long-term life in space is not something human beings have ever truly done. We have visited space. We have stayed for months at a time aboard the International Space Station, conducting experiments, maintaining equipment, exercising rigorously to slow the inevitable loss of bone density and muscle mass that comes from living without gravity. The longest continuous human spaceflight on record is just under a year. And the physical toll of even that duration, on the cardiovascular system, on vision, on the skeleton, on fluid distribution in the body, is significant and not fully understood. These are visits. Extended ones, carried out by carefully selected, highly trained individuals in a purpose-built environment continuously resupplied from below. They are not, in any meaningful sense, a model for what it would mean for humanity to live in space permanently, without a planet to return to. If Earth disappeared, that return would no longer be an option. For the small number of people who happen to be aboard spacecraft or space stations at the moment of disappearance, and for any larger population that had managed to evacuate in a hypothetical scenario with advance warning, space would not be a destination or an adventure. It would simply be existence. The only existence available. What that would actually look like, practically and psychologically, is difficult to overstate. Food production in space requires energy, specialized equipment, and carefully controlled environments. The caloric needs of even a small population quickly exceed what any current or near-future space habitat could provide. Water must be recycled with extraordinary efficiency. Aboard the International Space Station, approximately 93% of water, including moisture recovered from exhaled breath and other sources, is reclaimed and reused. Even with that efficiency, the system is fragile and dependent on components that wear out and must be replaced. Air must be continuously processed. Carbon dioxide must be scrubbed. Oxygen must be generated or carried in supply. Every single thing that Earth did for free, every function of the atmosphere, the water cycle, the soil, the living ecosystems, would need to be replicated mechanically, artificially, at enormous cost and complexity, just to keep a small number of people alive for a short period of time. And then there's the question of what that life would be like. Not just physically, but in every other sense. Human beings are social, cultural, environmental creatures. We build meaning from the world around us. Landscape, weather, seasons, natural light, open spaces, the presence of other species, the feel of soil and wind and rain, these are not luxuries. They are deeply embedded in how we experience being alive. The psychological literature on isolation, confinement, and sensory deprivation is extensive, and it is not encouraging. Even with every physical need met, the human mind does not thrive indefinitely in a small, enclosed, artificial environment. Long-term space habitation, in the absence of Earth, would be survival. It would be the continuation of biological life. But it would be a profoundly diminished version of what human existence on Earth actually was. And as people came to terms with the reality of that existence, something else would quietly fall away. Something so central to modern life that its absence would initially feel disorienting in a way that is hard to articulate. Money would become useless. Not gradually. Not through economic collapse in the familiar sense. But fundamentally, structurally, categorically useless. Money is a system of exchange built on the assumption of scarcity within an economy, a way of distributing resources, services, and goods among a population competing for them. It works because there is something to buy, somewhere to spend, a society within which transactions can take place. It works because there is property to own, infrastructure to pay for, production systems to compensate. In the void of space, with no planet, no ecosystem, no property, no infrastructure beyond the bare minimum required for survival, the entire conceptual framework that gives money its meaning would simply dissolve. What would you buy? From whom? With what guarantee of enforcement? In a small group of survivors aboard a spacecraft, the currency would be skills, labor, cooperation, and the physical resources available on the vessel. Not dollars or euros or yuan or any other token of an economic system built around a civilization that no longer existed. The wealth accumulated over lifetimes, the savings accounts, the property portfolios, the investment funds, the stock holdings, the entire elaborate architecture of human financial systems built up over centuries, would be worthless. Not devalued. Not inflated away. Simply and completely without meaning, in a context where the institutions and agreements that gave them value had ceased to exist along with the planet that hosted them. It is one of the more quietly vertiginous aspects of imagining Earth's disappearance, the realization of how many things we treat as fundamental and permanent are, in fact, constructs. Agreements. Systems that work only as long as the civilization maintaining them continues to function. Earth gone, civilization gone. Civilization gone, money gone. What remains is only what is real in the most immediate, physical sense. Air, water, food, warmth, human connection. Which brings us to a number that is, in its own way, as striking as any of the physical facts we have considered so far. Scientists and sustainability researchers have calculated that if every human being on Earth were to live at the average consumption level of a current high-income country, the resource use, the energy consumption, the land use, the waste production, the planet would need to be approximately 5 times larger than it is. Or rather, we would need the equivalent of 5 Earths to sustainably support that lifestyle for the current global population. We have one. This is not a new observation. It has been made in various forms for decades, by ecologists, economists, and environmental scientists. The concept of an ecological footprint, the amount of biologically productive land and water area required to produce the resources a population consumes and to absorb the waste it generates, makes this disparity visible in concrete terms. And the calculation is stark. The lifestyle that significant portions of humanity currently enjoy, and that much of the rest of humanity reasonably aspires to, is only possible because we are drawing on natural systems faster than they can replenish themselves. In the scenario where Earth disappears, this calculation becomes irrelevant in one sense: there is no Earth, so there is nothing to sustain. But it is deeply relevant in another sense, as a measure of how far human civilization had drifted from any sustainable relationship with the planet it depended on. The disappearance of Earth, in this light, is not only a physical event but a kind of final accounting, a moment when the gap between what we had and what we were using it for becomes impossible to ignore. Now, the story of what Earth is, and what its disappearance would mean, cannot be fully told without considering the long, ongoing story of life's fragility on this planet. Because Earth is not simply a stable platform for life. It is a dynamic, often violent environment in which life has struggled, adapted, proliferated, and repeatedly faced catastrophic loss. Every year, on average, approximately 2 vertebrate species go extinct. Not due to ancient geological events or asteroid impacts, but in the present era, in the current world, as a result of pressures predominantly caused by one species among the millions that share the planet. Vertebrates, fish, amphibians, reptiles, birds, mammals, are the animals we tend to know best, partly because we are vertebrates ourselves. They are the most visible component of a much larger biodiversity crisis that extends to invertebrates, plants, fungi, and microbial life. But vertebrates serve as a useful indicator, because they are the most thoroughly monitored group of animals on Earth. And the monitoring tells a consistent story. Since the mid-20th century, the total number of individual wild animals on Earth has declined by approximately 50%. Not 50% of species, 50% of individuals. Half of the wild animal life that existed on Earth around 1970 is gone. The oceans have fewer fish. The skies have fewer birds. The forests have fewer mammals. The rivers and wetlands have fewer amphibians. The sheer abundance of life, that sense of a world teeming with creatures in every habitat, has been dramatically reduced within the span of a single human lifetime. Amphibians are perhaps the most concerning group. Frogs, salamanders, and caecilian, animals that have survived on Earth for over 300 million years, that lived through the extinction event that killed the dinosaurs, are currently facing a crisis unlike any they have encountered before. Approximately 41% of all amphibian species are now classified as threatened with extinction. Many have already been lost. The causes are multiple: habitat destruction, disease, pollution, climate shifts, but the rate of decline is unprecedented in the amphibian fossil record. The current elevated rate of extinction across all species groups is thought to have peaked roughly a century ago, as industrialization accelerated habitat conversion and human populations expanded rapidly into previously wild areas. But it has remained significantly above background extinction rates, the natural baseline rate at which species disappear over geological time, throughout the 20th and into the 21st century. The single most significant driver of these losses is habitat destruction. When a forest is cleared, a wetland drained, a coral reef smothered by sediment, or a grassland converted to agriculture, the species that depended on that habitat do not simply move elsewhere. Often, there is nowhere else to go. The habitat is gone, and the species that relied on it either adapt rapidly, which most cannot do on human timescales, or they disappear. It is worth noting, carefully and honestly, that the relationship between climate change and extinction is more complex than is sometimes presented. While climate change is a genuine and growing threat to biodiversity, and is projected to become increasingly significant over the coming decades, current scientific evidence does not show that it has been the primary driver of the extinctions that have already occurred. Habitat loss has been, by a considerable margin, the dominant factor. This distinction matters, not to minimize climate concerns, but because understanding the actual causes of biodiversity loss is essential to addressing them effectively. And yet, against this backdrop of loss and fragility, there is a story that offers something different. Something that speaks to life's extraordinary resilience, and to the possibility of survival under conditions that seem almost incompatible with it. The Permian-Triassic extinction event, which occurred approximately 252 million years ago, is the most severe mass extinction in Earth's history. It is sometimes called the Great Dying, and the name is earned. Estimates suggest that somewhere between 90 and 96% of all marine species were lost. Approximately 70% of terrestrial vertebrate species disappeared. Entire taxonomic groups that had existed for hundreds of millions of years were wiped out entirely. The recovery took millions of years. The causes are still debated, but the leading hypothesis involves massive volcanic activity in what is now Siberia, the Siberian Traps, an enormous outpouring of lava and gas that released staggering quantities of carbon dioxide, sulfur dioxide, and other compounds into the atmosphere over a geologically brief period. The resulting climate disruption, ocean acidification, rapid warming, oxygen depletion in marine environments, collapse of food chains, was comprehensive and global. And yet life survived. Not comfortably. Not abundantly. But in pockets, in refugia, small areas where local conditions remained marginally more habitable than the devastated world around them. Protected bays, deep water environments, isolated highland areas. These became lifeboats. And from those lifeboats, slowly, over millions of years, life expanded again. Diversified again. filled the emptied ecological niches with new forms, new species, new relationships. Every animal alive today, including every human being, is descended from organisms that survived the Great Dying. Every lineage on Earth passed through that bottleneck and came out the other side. Life did not merely endure the deadliest extinction event in the planet's history. It ultimately flourished again, producing a world of biological complexity that in some respects exceeded what came before. This is not a reason for complacency about the losses happening now. The species going extinct today will not come back. The genetic information encoded in them is gone permanently. The recovery from a major extinction event takes millions of years, and the species that fill the ecological landscape afterward are not the same ones that were lost. They are new, evolved from the survivors, filling roles but not replacing what was there before. But it is a testament to something. To the depth of life's grip on this planet. To the way biology finds cracks and corners and marginal habitats and persists. To the fact that even the worst catastrophe Earth has ever experienced could not extinguish the living world entirely. Earth, it turns out, is very hard to kill. Harder, perhaps, than we sometimes imagine when we contemplate the fragility of individual species or ecosystems. The planet has been through impacts, volcanic winters, glaciations, ocean anoxia, and radical atmospheric shifts. Each time, life has been diminished. Each time, it has returned. The only scenario in which that resilience would count for nothing is the one we have been considering all along. Not a catastrophe that life must survive and recover from, but a disappearance so complete that there is no planet left to recover on. No refuge. No bottleneck. No slow, patient rebuilding over millions of years. Just the absence of a world that, for all its violence and all its fragility, had proven remarkably, stubbornly, beautifully alive. Something is happening right now, in the living world around us, that scientists have been documenting for decades with increasing concern and increasing clarity. We are living through a mass extinction event. Not a past one, recorded in the fossil record and studied from a safe historical distance. Not the Permian Triassic, not the end Cretaceous that took the non-avian dinosaurs. This one is present tense. It is ongoing. It is, by geological standards, extraordinarily rapid. And it is, in its primary causes, the product of the activity of a single species that has been on this planet for an eye blink of geological time. The term sixth mass extinction has entered scientific literature with enough consistency and enough supporting evidence that it is no longer a fringe position or an alarmist claim. It is the considered assessment of a broad scientific consensus, based on measured rates of species loss compared against the background extinction rate, the natural baseline pace at which species disappear over geological time. The current rate of extinction is estimated to be somewhere between 100 and 1,000 times higher than that background rate, depending on the taxonomic group being measured and the methodology used. For vertebrates, the most closely monitored group, the numbers are stark. Approximately 30% of all vertebrate species are currently experiencing population declines. Not just the famous ones. Not just the tigers and the elephants and the polar bears that appear on conservation posters. 30% across the full spectrum of vertebrate life: fish, reptiles, birds, mammals, amphibians. Species with names most people have never heard, living in habitats most people have never visited, performing ecological functions most people are entirely unaware of. Population decline does not always lead immediately to extinction. A species can decline significantly and still persist if the pressures driving the decline are reduced or reversed. But a population that has declined substantially is more vulnerable to further shocks, disease, extreme weather events, additional habitat loss, inbreeding in small isolated populations. The trajectory, for many of these species, is one that scientists describe with the language of emergency. We are not watching the beginning of this process. We are watching a process that has been building for centuries, accelerating through industrialization, and reaching a particularly acute phase in the modern era. The diversity of life on Earth that exists today is already a diminished version of what existed 200 years ago, which was already diminished from what existed 500 years ago. The baseline keeps shifting, and with each generation, what seems normal, the abundance of wildlife, the variety of species in a local ecosystem, is recalibrated downward. This is the world in which we are asking the question of what would happen if the Earth disappeared. Not a pristine, untouched world of maximum biological richness. But this world, this particular, complicated, beautiful, damaged, still astonishing world, at this particular moment in its history. And now, having spent considerable time with the physical, biological, ecological, and human dimensions of Earth's disappearance, it is worth stepping back from all of that. Stepping back very far. Far enough to ask not what would happen, but what it would mean. There is a principle in physics, one of the most fundamental and well-tested statements we have about the behavior of matter and energy, that says this: matter cannot be created from nothing, and matter cannot be destroyed into nothing. It can change form. It can transform from one state to another, solid to liquid to gas, matter to energy and back again under the right conditions. But the total amount of matter and energy in a closed system remains constant. In the scenario we have been exploring, the sudden, complete disappearance of Earth, this principle creates an immediate and irresolvable tension with physics as we understand it. True disappearance, in the sense of matter ceasing to exist entirely, is not something that happens in the known universe. Atoms do not simply vanish. Mass does not dissolve into nothingness. What this means, philosophically, is that the scenario we have been imagining is in some sense a thought experiment at the edge of physics, a hypothetical that requires us to suspend one of the most robust laws we have. We are not describing something that could happen within the known rules of the universe. We are describing something categorically different, an erasure. And the fact that physics has no mechanism for it is itself telling. It tells us something about how permanent matter actually is. The atoms in your body right now have existed since the early universe. Most of the hydrogen in your body formed within the first few minutes after the Big Bang, almost 14 billion years ago. The heavier elements, the carbon, the oxygen, the calcium, the iron, were forged in the cores of stars that lived and died long before the sun formed. You are, in the most literal physical sense, made of ancient star material. And that material will not disappear when you die. It will disperse, transform, cycle through the biosphere and eventually through geological and cosmic processes, but it will persist. Earth's matter is the same. If the planet could not simply vanish, if we follow the physics honestly, then the atoms of Earth would continue to exist somewhere, in some form, for as long as the universe itself endures. The planet as an organized structure, as a world, might be gone. But the matter would remain, transformed and dispersed, contributing to whatever processes the universe undertook next with it. There is something quietly consoling about that, even in the context of a thought experiment about disappearance. But stepping further back still, to the largest possible scale, the universe itself would not notice. This is not a poetic exaggeration. It is a statement about scale that is genuinely difficult to hold in the mind. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Many of those stars have planets. The Milky Way alone, our galaxy, the one containing our Sun and our solar system, is approximately 100,000 light-years across, and contains somewhere between 100 and 400 billion stars. Earth is one planet, orbiting one of those stars, in one of the Milky Way's spiral arms, in one galaxy among 2 trillion. The disappearance of Earth would not be detectable from the nearest star system, Alpha Centauri, approximately 4 light-years away. Not because the instruments aren't sensitive enough, though that's also true, but because there would be no signal to detect. No explosion, no flash of radiation, no gravitational wave. In the scenario of true disappearance, there would simply be an absence where something had been. An absence, at interstellar distances, is indistinguishable from the vast emptiness that already characterizes most of space. The universe would continue its expansion. Galaxies would continue their slow drift apart. Stars would continue their billions of years-long lives. Black holes would continue their patient accumulation of matter. The cosmic microwave background radiation, the afterglow of the Big Bang itself, now cooled to just a few degrees above absolute zero, would continue filling all of space with its faint, ancient warmth. None of it would pause. None of it would register the loss of one small, warm, wet, inhabited world in an unremarkable corner of one average galaxy. And yet, what that small world contained, what made it different from the hundreds of billions of other objects orbiting the hundreds of billions of other stars in this one galaxy, was something that, as far as all of our searching has revealed, exists nowhere else within our observational reach. Awareness. Curiosity. The capacity to look up at the night sky and wonder about it. To build instruments to measure it. To develop mathematics capable of describing it. To ask questions about it that take generations to answer. To feel, in the presence of it, something that might be called awe. The universe's indifference to Earth's disappearance is not a diminishment of what Earth was. It is simply a fact about scale. The universe does not register significance. It does not keep records of what was remarkable. It does not mourn. We do. Or we did. And that capacity, to find things remarkable, to feel the weight of loss, To understand what it would mean for something extraordinary to be gone is itself one of the most extraordinary things Earth ever produced. The fragility of human existence, seen clearly, is almost vertiginous. The number of precise conditions required for this planet to be habitable, the right distance from the right kind of star, the right planetary mass, the right atmospheric composition, the right presence of liquid water, the right magnetic field, the right geological activity, the right evolutionary history spanning billions of years, is staggering. The probability of any single one of those conditions being met by chance is small. The probability of all of them being met simultaneously, on the same world, at the same time, is small enough that it has led some scientists and philosophers to describe Earth as something close to miraculous. Not in a supernatural sense. In a statistical sense. In the sense that the conditions required for a planet like this to exist and to sustain complex life for billions of years represent an extraordinary convergence of physical, chemical, geological, and biological circumstances, each of which could have been different, and most of which, across the universe, apparently are. The fragility is not just that Earth could disappear. It is that it was here at all. Now consider the light. Right now, at this moment, light is leaving the surface of the sun and traveling toward Earth at 300,000 kilometers per second. That light will cross approximately 150 million kilometers of empty space before it reaches us. And that journey, at the speed of light, takes approximately 8 minutes. This means that the sunlight falling on your face at any given moment left the sun 8 minutes ago. The sunrise you might watch tomorrow morning will have begun its journey across space before you wake up. By the time the light reaches you, the moment of its emission is already history. This 8-minute travel time defines a boundary we call 1 astronomical unit, 1 AU. It is the standard unit used to describe distances within our solar system. Mars is about 1.5 AU from the Sun. Jupiter is about 5. Neptune is 30. Voyager 1, the farthest human-made object, is now more than 160 AU from the Sun, and it has been traveling since 1977. 1 AU is the distance between Earth and Sun, defined by the time it takes light to cover it. If Earth disappeared, the Sun would not know immediately. The gravitational effect of Earth's disappearance would propagate outward at the speed of light, and so for 8 minutes, the Sun's gravitational model would still include a planet that no longer existed. For 8 minutes, from the Sun's perspective, everything would appear normal. Then, imperceptibly, the tiny gravitational contribution of Earth would simply no longer be present. The adjustment would be immeasurably small. The Sun would not react. But those 8 minutes, that delay between disappearance and its propagation to the nearest star, is a reminder of how strange and absolute the speed of light truly is. Even information about catastrophe travels at a finite speed. And then there is the name. Of all the planets in our solar system, Earth is the only one not named after a figure from Roman or Greek mythology. Jupiter, Saturn, Mars, Venus, Mercury, Uranus, Neptune, all carry the names of gods and mythological figures, a tradition that extends back through centuries of astronomy. Earth is different. The word Earth comes from Old English and Germanic roots, the word Ur in Old English, the word Erde in Old High German. Both mean, essentially, ground. Soil. The surface beneath your feet. We named our planet after what it was to us, at the most immediate and physical level. Not a god. Not a celestial power. Just the ground. There is something in that which feels entirely right. Before we had any concept of the planet as a planet, before we understood it was a sphere, before we knew it orbited the sun, before we had any sense of its place in a universe of billions of galaxies, we knew the ground. We knew the feeling of it under our feet. We knew it grew things we could eat, held water we could drink, sheltered us when we dug into it or built upon it. The name is not poetic or aspirational. It is the most grounded name possible, in the most literal sense. Earth. Ground. The thing you stand on. And in a way, that plainness is more moving than any mythological name could be. It is the name given to a world by creatures who lived on its surface and knew it the way you know the floor of the room you grew up in. Intimately. Practically. Without distance or abstraction. When we speak of the earth disappearing, we are speaking of the ground disappearing. The thing beneath us. The oldest and most fundamental reference point of human experience. The word that meant home before the concept of home was ever formalized. Just ground. And without it, nothing to stand on. Nothing to call by that old, quiet, unassuming name.